Hello dosto, welcome to KP Academy once again. Here we have another numerical on cooling load calculation from the Mumbai University December 2016 paper. This problem was repeated again in same university paper, right? So in problem we have given condition that we have to maintain a hall or room at 24 degrees Celsius dryable temperature and 60% relative humidity. The outside condition is given 38 degrees Celsius dryable temperature and 28 degrees Celsius wet bulb temperature. Through any means we have some room sensible heat and room latent heat given, that is 46.4 kilowatt and 11.6 kilowatt. But again there is another thing that is given, the air infiltration. So through any means we have some air infiltrated into the room. The rate of that is what? 1200 meter cube per hour. We have coil temperature given to us 10 degrees Celsius and the quantity of air recirculated. That means room air is again recirculated over here and it is 60%, right? And it is circulated after the cooling coil. That means after the cooling coil we have this recirculated air, right? So that is what after the L point and I point we get this S point, that is supply condition, right? So that is what the data given to us. This is what the scenario that we have, right? So based on this one we have to find out what condition of air leaving the coil. That means the L point that we have to find out. Then condition of air entering the hall. The supply condition we have to find out. Mass per rate of air entering the cooler. That means how much amount of mass of that outside air is required to pass, right? Mass per rate of total air passing through the hall. What is the mass per rate of supply air? Bypass factor of the cooling coil and refrigeration load on the cooling coil in ton of refrigeration. So ton of refrigeration of this cooling coil that we have to find out. So this is what we have the condition given in our numerical. So that is what given data. So based on this given data we can plot this point I point and O point on the psychrometry chart. So this is what psychrometry chart we have. So we have this flow diagram once again over here. The room condition 24 degrees Celsius dryable temperature and 60% RH. Outside condition 38 degrees Celsius and 28 degrees Celsius WBT, right? So based on this we can easily plot this point O and I like this. So this is inside condition that we have to maintain and this is what outside condition, that is what available with us, right? Now in order to find out what total room sensible heat is and room latent heat is, we have to find out what is the contribution of infiltration air, because in numerical it is given that there is an infiltration air also which actually contributes the room sensible heat and room latent heat, right? So in order to find out how much amount of the contribution of that infiltration air is into the room sensible heat and room latent heat, we have to find out, we have to locate the point like this. What is that? Draw vertically a line starting from O point and horizontal from I point. Here we go like this, right? Now O to this point, whatever the contribution is which contributes the latent heat, because of that only WBT specific humidity is increasing. That means latent heat contribution is there. And from I to A, let us say यहाँ पे A point है. So from I to A there is only change in the dryable temperature. There is no change in the specific humidity. That means this only contributes the sensible heat, right? So if I now note the point of enthalpies of I point, A point and O point, I'll get those enthalpies like this. So if I take the enthalpy difference of I and A now, that is actually the contribution of sensible heat, right? And if I take the enthalpy difference of O and A, that is nothing but the latent heat contribution, right, by the infiltration air, right? So this is how we can find out the contribution of infiltration air into the room, right? So these are the enthalpies that you can note down. where we have to note down these enthalpies corresponding to this O, A and I point. So here is we have the enthalpy scale. So corresponding to I point, we have enthalpy as 53, right? Corresponding to O point, we have enthalpy as 90, and corresponding to A point, we have enthalpy as 68 kilojoule per kg, right? Along with this one, we require actually the specific volume of O point also, that is what outside condition. The specific volume of outside air is also required. Okay. So how to find out that? So you can see here, this is what the specific volume line, and the value of that is what 0.90. Here we have another specific volume line, the value of that is what 0.95, right? So if I divide this space between these two lines in 5 cases, 5 lines, then corresponding to O point, we will have the specific volume as 0.91. So this is what 0.91 specific volume of outside air. Okay. Now, what exactly we want to find out is what mass of infiltration air, mass of infiltrated air. How to do that? Mass of infiltrated air equal to volume flow rate of the air, that is infiltration air, divided by specific volume. That is what the fundamentals to calculate the mass of air, right? So in our numerical, it is given the volume flow rate of the infiltration air is how much? 1200 meter cube per hour. But now I have here value in 20 meter cube per minute. So in minute I have given here. So 20 meter cube per minute divided by specific volume that we have already calculated, 0.91. So if I calculate this, I'll get the value 21.978 kg per minute. So in second, 0.36 kg per second. Now with the help of this M1, we can easily find out what is the contribution of infiltration air as sensible heat and latent heat into the room. So sensible heat gain due to infiltration air, M1 multiplied by enthalpy difference of A and I point. Why A and I point? Already we have discussed that, because when I take the enthalpy difference of A and I point, which exactly contributes the sensible heat, because there is only temperature change, not the specific volume. That's why A and I point, right? So we have the enthalpy of A point as 68 kilojoule, I point as 53. So if I calculate this, I'll get the sensible heat gain due to infiltration air as 5.49 kilowatt, which exactly adds into the room sensible heat. So we have already given room sensible heat, that is load available in a room. In our numerical, it is given 46.4. But this infiltration air again adds this value, that is how much? 5.49. So total room sensible heat now becomes 51.89 kilowatt. Similarly, latent heat gain due to infiltration air as M1 multiplied by HO minus HA. The enthalpy of O point is 90, that is what outside condition, right? And A point as 68. So here we have the latent heat gain due to infiltrated air as 8.05 kilowatt, right? Similarly, total latent heat gain in a room is how much? 11.6, which is already given in our numerical as a latent heat load in our room. But infiltration air also contribute that, the amount 8.05. So total latent heat gain in a room is how much? 19.65 kilowatt. So here we have room sensible heat, here we have room latent heat. Now let us find out the room sensible heat factor. Okay. So room sensible heat factor, we have room sensible heat factor can be calculated like this: room sensible heat divided by room total heat. How much is the room total heat? The sum of room sensible heat plus room latent heat, right? So if I put these values over here, I'll get directly the value of room sensible heat factor as 0.725. Now with the help of this room sensible heat factor, let us find out other points like this on the psychrometry chart, right? Now here we have ADP given in our numerical, the coil ADP, apparatus dew point temperature 10 degrees Celsius, that I have located over here on the saturation line. So this is what the saturation line we have. On this we have this 10 degrees Celsius as a ADP. Now you can see here there is a sensible heat factor, and we have already calculated that room sensible heat factor is how much? 0.725. So corresponding to this point now, 0.725, we can mark this point over here, right? And we draw a line starting from this point up to the reference point. So that is what reference point over here. It is marked with the circle, right? So condition of this reference point is what? 26 degrees Celsius dryable temperature and 50% RH. It is available on the psychrometric chart. If it is not, then you can consider that as a 26 degrees Celsius dryable temperature and 50% RH. So what we do, we draw a line from this reference point and the point that we have marked on the sensible heat factor scale corresponding to room sensible heat factor. So in our case, it is 0.725. So here we have the line, that is yellow line, called as reference line. Now parallel to this line, we pass that line, another line from I point. So parallel to this reference line, we pass a line, we draw a line starting from this I point this side. Okay, you can see this is the black line now. Okay, so this black line is nothing but what? Room sensible heat factor line. Okay, which is passing through this I point. Now you can see here there is an outside air which directly pass on the cooling coil, right? And then we get the L condition, right, outside the cooling coil, right? So this is what outside condition that we have. This air directly pass on the ADP and we get the L point. That is what? The air coming out from the cooling coil. So that L condition we will get on the line joining this ADP and O point. So let us draw this line joining this ADP and O. So on this ADP and O line, जो भी यहाँ पे draw किया है, that is called as Gshf line, grand sensible heat factor line. So on this grand sensible heat factor line, we will get this L point actually, the condition of air leaving the cooling coil, right? What is that exactly? The line, these two lines, black line and this line, grand sensible heat factor line, right, intersect at this point. That is nothing but the L point. Okay, so here we go. So corresponding to this point now, whatever the temperature is, enthalpy is, relative humidity is now the condition of air leaving the cooling coil. So the condition of air leaving the cooling coil is how much? The 15 degrees Celsius dryable temperature. So here we can see 15 degrees Celsius dryable temperature. And relative humidity is how much? So this line is of 90% relative humidity. So corresponding to this point, it may be near about 92%, right? This way. So the condition of air leaving the cooling coil is how much? 15 degrees Celsius dryable temperature, 92% relative humidity, and enthalpy is 40 kilojoule per kg. Okay. How enthalpy? We have calculated this on the enthalpy scale like this. So corresponding to this L point, the enthalpy is 40 kilojoule per kg. Okay. Next. Here we have that already we calculated that. So that is what the second point that we have to calculate from our numerical, right? Now let us find out the condition of air entering the hall. Okay. मतलब क्या है? Yes condition. The condition of air entering the hall. मतलब supply condition. मतलब yes point का मुझे temperature, relative humidity, everything that we have to calculate. अब यहाँ पे देख सकते हो आप, in this case, this yes point is actually after the mixing of two streams, that is L stream and I stream. I stream is what? Again room air which is recirculated. Okay, and L is what? The condition of air after the cooling coil. So these two streams comes together and we get the supply condition, right? Now the supply condition dryable temperature can be easily find out using the adiabatic mixing, considering this L and I stream as a adiabatic mixing. So when there is a adiabatic mixing, we have the formula given to us, that is what? TS, that is supply condition, equal to Ti, the temperature of I, that is recirculated air, mass of that I, plus TL, temperature of this L condition, mass of this L divided by Mi plus Ml. Now in this case, we do not have the Mi and Ml actually, but we have the percentage of that air, right? So in this scenario, we can find out this mass of I and mass of L, right? So contribution of return air is how much? 60%. That's why I'm considering it as a 0.6, and contribution of this is what? ml 0.4. So here we can find out these values. So Ti, that is what inside condition we have 24 degrees Celsius. So 24 degrees Celsius multiplied by 0.6 plus 15 degrees Celsius, the condition of this TL, that already we have calculated that. Okay. So if I put these values over here, I'll get the TS, that is supply temperature, as a 20.4 degrees Celsius. Okay. The supply air temperature is how much? 20.4 degree Celsius. So let us now mark this point on the psychrometry chart. Where exactly it is? It is over here. You can see here the drivable temperature is 20 degrees Celsius and our S condition is what? 20.4. So corresponding to that, I have this S point, which will be on the room sensible heat factor line, isn't it? It will be on the room sensible heat factor line, right? Because L stream and I stream are joining together, and then we are getting this S stream. That means the line joining this L point and I point, we will have this S point, right? That's why this S point we will get on the room sensible heat factor line, right? So this is what S point, that is supply condition. So corresponding to this S point, now we can calculate other points also, like enthalpy we can calculate, like relative humidity we can calculate, right? So enthalpy is near about, how much it is? 40 kilojoule per kg, corresponding to S point. Oh, actually it is 47. It's not a 40. This is what L point actually given, but it should be corresponding to S point. It should be 47 something, right? Relative humidity is 72%. You can see this is for the line of 70% is relative humidity, and corresponding to this S point, now we have 72% what we say relative humidity, right? So this way we can find out the condition of air entering the hall or room, right? Now the next part we have to find out is mass of air entering the cooling coil, then mass of total air entering the hall, bypass factor, and refrigeration load on the cooling coil. So these are the different parameters that we have to find out. Let me just adjust this. So here we have flow diagram over here again, right? Now till now whatever we have calculated, these are the points that we have again: O point enthalpy, I point enthalpy, room sensible heat, room latent heat, the condition of air entering the hall, and condition of air leaving the coil. So these are the parameters that we have already calculated. Now we have to find out what these different parameters. So first of all, mass of air entering the cooling coil. So mass of air entering the cooling coil means what? Outside air mass which is passing over the cooling coil, that we have to find out. Now this mass will be the mass of L point again, because there is only one stream. Whatever the outside air is passing over the cooling coil, the same air is over here also. So mass will be the same at L point. So after the cooling coil, whatever the condition of the air of this L point is, this is nothing but taking care of the load of this room. Okay, whatever this condition of L air, that is what L now is conditioned air. It is conditioned air. So the contribution of this conditioned air is what? To take the load of this room, so that we can maintain the temperature of room as 24 degrees Celsius and 60% RH. That means this L air absorbs the total heat of the room, isn't it? So total heat of the room, that is absorbed by this L air. Okay, so that is the reason total room heat will be equal to mass of the air, that is conditioned air at L point, right, and enthalpy difference of this L point and I point. As this air taking care of the room heat. That's why we have to take the enthalpy difference of room air and L air. Okay, so that's why total room heat equal to ML multiplied by HI minus HL. So what is HI? 53. What is HL? HL already we have calculated that it is 40 kilojoule per kg. So HL is equal to 40 kilojoule per kg. Okay. Now what is total room heat? It is nothing but room sensible heat and room latent heat. So sensible heat is 51.89 and latent heat is 19.65. So if you put this all the values, unknown is only ML. So I'll get the ML as 5.5 kilojoule per kg per second. Okay. Now if I calculate this in per minute basis, so 5.5 multiplied by 60, so our value is 330.184 kg per minute. This is nothing but the mass of air entering the cooling coil or entering the cooler. Okay. Now next we have to find out is what? Mass of total air entering the hall or room. How much amount of mass of air entering the hall is, that we have to find out. Now actually there are two streams coming from L side and I side, and together they are getting as a S point, that means supply air, for which we have to find out now mass, right? So already we have calculated that how much amount of mass of air entering the cooling coil is, that is what? L mass, right? So considering that only, we have to find out this mass of total air entering the hall. How much it is? It is nothing but this mass, this air, right, plus 60% of this again supply air, isn't it? Whatever the supply air is supplied into the room, whatever the mass of this supplied air is, it is again recirculated. 60% of that is again recirculated, isn't it? And remaining is what? This mass of air entering the cooling coil, right? So that is the reason mass of air entering the cooling coil, that is 330.184, that already we have calculated that, right, plus mass of supply air which is recirculated. So how much it is circulated? It is 60%. That's why 0.6 of mass of air which is circulated equal to total mass of supply air, isn't it? So that's why if I calculate this, only unknown is here MS, that is supply air. So MS is equal to how much? 825.45 kg per minute. Okay. So that is what mass of total air entering the hall is. That means this air which is entering into the room. Next is bypass factor. Bypass factor of the cooling coil. It is very simple now to find out this bypass factor. We have something over here. Now let's say so the bypass factor, it is very easy to find out this formula. It is not required to remember this formula actually, right? So what exactly is the bypass factor? Let us understand that, right? So outside temperature is how much? 38 degrees Celsius. Let us say यहाँ पे TDO mark कर रहा हूँ मैं, right? And there is a ADP, isn't it? There is a ADP over here. When this outside air passes over the ADP, the temperature of air drops down like this, but the ADP will remain same. So at the exit now, the temperature will be equal to TL, right? And here the temperature of coil again ADP. Okay, it will not, the air temperature will not be equal to ADP because it has bypass factor. The coil has some bypass factor. So that is the reason we are not getting the coil temperature as a equal to ADP, right? So what would be the bypass factor in this case? So bypass factor will be equal to the temperature difference of these two divided by temperature difference of these two. Okay, so that's why TL minus ADP divided by TDO minus ADP. So that is how we can find out the bypass factor of the cooling coil. The same is written over here, right? So bypass factor is equal to TL minus ADP upon TDO minus ADP. So TL is calculated by us, that is what, 15 degrees Celsius. So 15, ADP of the coil is 10, TDO is 38, that is given in our numerical itself, right? TDO, that is 38, right? So if I put all these values, bypass factor is equal to 0.18. Okay. And finally, we have refrigeration load on the cooling coil as ML multiplied by HO minus HL. Total load on the cooling coil is what? ML, that is what, the mass of air entering the cooling coil. Mass of air entering the cooling coil. That means this one only. Okay. So ML multiplied by HO minus HL. Right. So enthalpy difference of these two. That is what the total refrigeration load on the cooling coil. Right. So HO is 90 kilojoule per kg. HL is this is what, 40. So if I put all those values, we will get the value, that is what, load on the cooling coil as 275 किलोवाट. अगर हम इसको डिवाइड करेंगे 3.5 से, we will get that in ton of refrigeration. So total refrigeration load on the cooling coil is 78.57 ton of refrigeration. So this way we can find out all those values using the psychrometry. That is what the problem on cooling load calculation. Thank you.